We're going to talk about Thevenin's theorem today, but before we do, there's that question on melts. I want you to find the voltage VOC. At the moment, nothing to do with Thevenin. We'll see what it has to do with Thevenin later, but for the moment, a little bit of circuit analysis on a reasonably simple circuit. What is the voltage VOC? You can certainly chat, do it together. Any thoughts? Question? That looks good to me. That looks good. Any ideas? What? Don't what? What do you think? Can you do it? How did you get that? Perfect. No, you only said it to me, so you don't get around it. Okay, this is clearly this is split voters. It's quite definitely split voters. Is that enough time? I'll lock that now. I'll lock it in 10. 10, 9, 8, 7, 6, 5. What's 3, 4, 2. Oh, jeez, that's a lot of responses. All right, I'll lock it there. So quiet, please. About a third of the respondents said it was 3 volts, and about a third said 9 volts, and quite a few said minus 3 volts. So that's very fairly random. Let's have a look. One thing, I could do Kirchhoff's voltage law around the outer loop. That's what maybe what I'll do. We used to go in clockwise, so we could do this. Go here, 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 and back to there. What does that give us starting here? Well, I would have VOC plus minus in that direction. The voltage I'm looking for, VOC. And then I move along here, there's nothing, there's nothing, there's nothing. I hit a resistor of 1K. Well, I've said let's call that current flowing through at I. I don't know what it is yet. Maybe I do, but for the moment I'm going to call it I. So I will have plus 1Ki, and then there's also 2K with the same current in it, so they add up. So I have 3K times I, and now I'm up here, moving here. I hit the 3 volt source, hitting the negative first, so I write minus 3 volts equals 0. So VOC would be equal to 3 minus 3K times I. But what's I? Well, look at this. I've got 2 milliamps going up here. How much current goes in that direction? None. This is an open circuit here. Infinite resistance. No current will go in that direction, so therefore the whole 2 milliamps will flow around that way. So what's I? Minus 2. Just the sign convention was the other way around. I is minus 2 milliamps. Therefore VOC will equal 3 minus 3K by minus 2 milliamps, which equals 9 volts. So clearly there were some concepts in there that some people wanted to just say it was the 3 volts, maybe because of the 3 volt battery up there. But how could you do that? What's the voltage across the current source? VOC would be 3 volts plus the voltage on the current source. And you don't know what the voltage on the current source is, you've got to work it out. So in fact, we had to do it using Ohm's law. So something to think about, but so about a third of you got that as 9 volts. Hopefully now that I've worked through it, you can see where you went wrong if you put 3 volts or minus 3 volts or 0 volts. Okay, now do that one. I want the current. I've labelled it ISC, and that, if you can't see the arrow, is going down the same circuit, but instead of leaving the terminals, if you like, open circuited and finding the voltage, I've now short circuited it, and I'm interested in finding the current, but the rest of the circuit is the same. So that should be open now to work on. I don't think, some of you might be able to, but I couldn't do it instantly. It does need a little bit of thought to do it. So if you sort of instantly wrote down the answer, you're either quicker than me, which is very possible, or you've maybe done something not quite right. So what is ISC? All we have is our basic circuit analysis techniques, remember. Ohm's law, KCL, KVL. In more complex circuits, we can systematically apply those to do nodal and loop. But really, we've got Kirchhoff's current law, voltage law, and Ohm's law. The only things you've got to apply there. That's about 40 responses. We'll leave it open a little bit longer. couldn't do it with that paper. Any thoughts, guys? What be considered a short? It is a short circuit. Yeah, that's in fact what the SC stands for. Yeah, so we have, if I saw those other things before that I measured VOC across the terminals, I left it in open circuit state and found VOC, the open circuit voltage. Now I've shorted them and measured the current flow. And that's I short circuit. But just because it's a short doesn't instantly tell you the answer. Still got to do your circuit analysis. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, 2/3 of people now say 3 milliamps. 60 out of 90 say 3 milliamps. The next most popular one is 1 milliamp. One's 2 plus 1, one's 2 minus 1. So maybe there's only a sign difference between those two. So let's work through it. I'm going to do Kirchhoff's current law at that node. I don't know its voltage. Well, maybe I do, in fact, but I'm just going to say it's V1 at the moment. And I'm going to do Kirchhoff's current law. So I could say that current there is V1 divided by 3K. I have to better define ground, sorry. I'll call that ground and the top's at V1 with respect to it. V1 on 3K, that's that current. That current there would be minus 2 milliamps. And this current there, well, I'm going to this time put it as ISC because that's what I'm trying to find anyway. So plus ISC equals 0. Kirchhoff's current law. If I knew V1, then I could find ISC. Hang on, but what's V1? What's V1? There's a voltage source between ground and that node. It is minus 3 volts. If I trace up here, I go zoom, zoom, minus 3, and I'm at V1. That's like nodal analysis when there was a voltage source between ground and the node. V1 is minus 3 volts. Therefore, if I plug that in, I grab that there and go around there and plug it in there. I get minus 1 milliamp minus 2 milliamps plus ISC equals 0. Therefore, ISC equals 3 milliamps. Are there any questions about that? Happy to answer any questions. Nothing to do, well, it turns out this will have something to do with Thevenin, but at the moment I want to separate out that we're just doing circuit analysis, KCL, Ohm's law, that type of stuff, to find this voltage and this current, and we'll see later what that has to do with Thevenin. Stylish, yes. A student from last year sent this to me, or posted it on Facebook, I think. What do you think is special about this polo shirt? Any ideas? you can shoot this person with an Uzi machine gun and it will not get through. This is a bulletproof polo vest. It comes in 3 different protectivity strengths. One that just handles a pistol, but this one, the most strong, will handle an Uzi machine gun and a knife trying to stab you, and you will be safe. This is stylish and secure. It's by a Colombian designer, Miguel, not surprising perhaps. Is there anyone from Colombia here? There might be. No, you are? Do you know this guy, Miguel? Let's see, Miguel Caballero. Anyway, $10,000 though. That's the only problem. It's fairly expensive. This is the sort of stuff Obama wears, President, all the famous people. You don't know they're wearing it. For you guys, if you can't afford that, you might be able to get that though. That is a bulletproof backpack that you can wear to university. Be very stylish, and just in case. I don't know why the student sent it to me. Maybe suggested that I might need it. I don't know if that was the suggestion. I certainly hope not. The world leader in secure and stylish clothing, Miguel Caballero. All right, let's start talking about Thevenin. So there's a box. Shush, shush, shush. There's a box. It's a black box. You can't see what's inside it, but it's full of resistors in a particular series, parallel combinations of resistors. So I'll just, write some resistors there. Some combination of resistors all wired up. If you had to try and, work out what was in there, well, you could do tests on that thing. You could put different voltage sources on there and measure the current, or put current sources on there and measure the voltage. So suppose you do that, that's some element. You do things, you measure that voltage and you measure the current that flows as a result, V and I. You probe it and get all these different VI points. This is a test you could do in the lab. So if you do that, you could plot I against V, and it can only look like a slightly wiggly line through the origin. Meant to be a straight line through the origin. If that box is just full of resistors, that's all it can look like. The slope must be the equivalent resistance of that whatever combination of resistors you have. So I could replace everything that's in the box by one resistor equal to R equivalent, and it will have exactly the same VI relationship as whatever is in there. I can't tell the difference. That's all I can learn about inside the box from probing. It can only be a straight line through the origin, so all there is to know is the slope. That is the equivalent resistance that you found before for circuit combinations. Series, parallel combinations, you know how to calculate it if you could see the circuit. Well, if you couldn't see it, that's how you could do it. You just measure a couple of VI points. In fact, how many do you need to measure? Can anyone beat 2? You only need 1. Straight line through the origin, all you need is 1 point to specify it. I would have said 2 too, but I just thought actually you only need 1 because it's through the origin. You just measure 1, voltage and current, take their ratio, and you've got the equivalent resistance. That's another way to find equivalent resistance. So that's all right if you just have resistors. If the equation of that line was V equals minus R equivalent times I. V equals minus R equivalent times I. It's negative just because of the way we've defined the V and the I, because we said plus minus V with I flowing out. So that's why the slope is negative. Terrific. What if I put voltage sources and current sources in that box now? My circuit has more elements in there. It might have some resistors there, one there, but it also has voltage sources and maybe even some current sources wired up. I want to work out what's inside the box. Well, there's only so much I can do. I can again probe. I could put resistors or voltage sources or current sources there, producing a certain voltage and a certain current, exactly the same way. What can possibly happen to that VI relationship? What could be different about it? Well, I can tell you it's got to be a straight line. This is linearity. So what can happen? Offset. That's the only thing that can happen. It's got a slope, but it doesn't have to go through the origin now. It might look like that. That's all I can do as a result of putting in the sources. I can make it offset. But it doesn't matter what else is in there. It doesn't matter what's in there and in what configuration. That's all I can produce. It has to be a straight line. So the most I can get out of it is a straight line that doesn't necessarily pass through the origin. Now how many measurements would I need to make? 2. Exactly. Now I don't necessarily know I'm passing through the origin. So in general I measure 2 VI points and the straight line between them and I'm done. I've fully characterised what must be inside that box. So again, the slope is because of all the resistance, and that's minus R equivalent. But now, if you look there and there, I can have non-zero intercepts. If I just had resistors and there's no voltage, there's no current because it's a passive, entirely passive circuit. But if I put active elements in there, sources, it can mean that I don't have to just pass through the origin. I can't just use a resistor now. Yeah, sorry?
Does that include dependent sources as well?
Yep. You can also put dependent voltage and current sources in there as well. Doesn't matter what I do. If I put a diode in there, no. Different story. All these linear elements that we've been talking about, that's all you're going to get. And so you could fully characterise it with 2 measurements. What equivalent circuit could also produce that slope? Just the resistor, R equivalent, doesn't do it. So now, if I'm interested in finding equivalent circuits, just a resistor is clearly not enough. I need some other element to give me an offset. So I want you to have a little think. I'm going to draw 4 possible circuits and see which ones might be able to produce that type of response. Circuit A. Is that one? Could I replace what's in the box with that and get the right sort of relationship? B. Well, maybe I could do that. C. I could do a voltage source in parallel with the resistor, or D, I could do a current source. I want to be able to replace everything that was in the box, whatever it was, by one of these much simpler circuits. So by thinking a little bit about what you know about the voltage, so if I did this trick again and put some element there, I measured the voltage and I measured the current, would you be able to generate any slope and any offset from those different curves? So that's a Meltz question. Which one works? Which one works? That's now up on Meltz. So clearly the resistance is giving me the slope, but I added a current or a voltage source to give me some offset now. But do they all work? Or does only one of them work, two of them work? You can only pick one. But I'm glad there's no option for all, because it's not all of them, as a hint. It's certainly not all of them. There are two correct answers. You can't select two, but I can set two as correct. So you pick either one, you get it. Okay, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right, 37 out of 88 say A, a few say B, 31 say C, and 13 say D. Let's go to this one here, this B up here. I can put whatever I want there. What is that current? That current is whatever the current source is. It doesn't matter what element I put up there. The equation of this circuit, let's say this is 7 amps, that equation will be I equals 7 amps always. On the VI curve, it's either straight up. It is, that's straight up. I equals 7 amps no matter what. There's nothing to give it a slope. The resistor is irrelevant in that circuit. Remember what a current source does. It pumps out that much current regardless of what it's connected to, the terminals. It does not work. Its VI characteristic is straight up like that. I equals 7 amps. What about C? Quite a lot of you said this one looks good. What is the voltage across these terminals? If that is 6 volts. 6 volts, no matter what the value of the resistance. It is flat sitting there at 6 volts. That's not giving us this slope and the offset. It's just giving us an offset. That one may as well not have the resistor there because it does nothing. Same as B. Resistor may as well not be there. Just like a current source alone or a voltage source alone, that gives us the offset but doesn't give us the slope. The two that work are A and D. A parallel combination of a resistor and a current source, or a series combination of a voltage source and a resistor. So very quickly, plus minus. Let's call that VOC. R equivalent. So if I plot the IV characteristic of that, you can do it. It will look like that. This point here, what's that? that intercept where I equals 0. VOC, that is the voltage source. VOC is that intercept. The slope, you can see, will be minus REQ. You can do Kirchhoff's voltage law and you'll see that you will get this relationship between V and I for that circuit. So it works. We would be able to choose the right value of R equivalent and the right value of VOC to exactly match our measurements that we made. Similarly, this one also works. With this as REQ and that as ISC, what is this intercept? I short circuit. If I just shorted this, then the resistor R equivalent here, if I just shorted that, then the current that flows would be ISC. So that corresponds to that intercept there. So both of those work through appropriate choice of VOC or ISC. You can exactly match any characteristic that you'll get. But the other ones don't work. The top one is the Thevenin equivalent circuit. The bottom one is the Norton equivalent circuit. And this is Thevenin and Norton equivalent circuits. That's what the next two lectures are about. Conceptually, that's it. We just have to know, given any circuit, how do you replace it by the thing up the top? How do you replace it by the thing up the bottom? It turns out you've got to find the open circuit voltage and the short circuit current exactly as we did at the start of this lecture for a particular circuit. So in fact, we've done all the hard work to find the Thevenin equivalent circuits. Okay, so equivalence, we've already done it for resistors. Circuits just of resistors, we know how to replace it by an equivalent circuit. Thevenin's theorem tells us that we can replace any self-contained network of voltage current sources and resistors with an equivalent circuit. And that, just to make it clear, the thing inside this box is what we're replacing, and you can replace it by that, a series combination of a voltage source and a resistor. That's Thevenin's theorem. You've also seen what Norton's theorem is. Instead, a parallel combination of a current source and a resistor. But this one here is called the Thevenin equivalent circuit. It's named after Leon Charles Thevenin, who was a French telegraph engineer, a talented violinist, and he liked to fish and probably didn't mind eating fish either. The telegraph, his electrical telegraph, was the first long-distance way of communicating with electricity. And again, at the time, fairly amazing that you could have a wire running for several hundred kilometres and communicate information almost instantaneously over it. When it was first introduced in sort of the early 1800s, it was used for railway signalling so that they could keep trains safe. But then a particular message was sent. I think it was in 1845. This is a message that was sent over the telegraph. A murder has just been committed at Salt Hill, and the suspected murderer was seen to take a first-class ticket to London by the train which left Slough at 7:42 p.m. He is in the garb of a Quaker with a great coat on which reaches nearly down to his feet. He is in the least compartment of the second-class compartment. That message was sent when the train pulled up at London. The message was faster than the train, and he went off and they followed him and arrested him. As soon as that was done, all of a sudden, in the public's eye, the possibilities of this long-distance communication became great. Before it was just used for trains. But all of a sudden, a murderer was captured using the electrical telegraph, and it created a great deal of publicity. And off it went from there. Why do you want... So, quiet please. Why do you want to replace a big complex circuit by a simpler one? Well, it's nice, I think, to reduce all sorts of complicated stuff to a very simple circuit. If you wanted to repeatedly analyse some big complex circuit, maybe you've got a variable load on there and you're going to keep changing the load and you want to know what's going to happen rather than reanalyzing it or whatever the case may be. If I can replace what's in the box with that, I have a fairly simple circuit to analyse. And as I vary L, I'll very easily be able to work out what's going on. We'll see when we do circuits with capacitors and inductors later on that this notion of equivalent resistance or Thevenin resistance is also very handy there. Quiet, please. How do we find R Thev and V Thev? Remember, we've got to match this particular line. Well, we need two equations. We've already said that. We need sort of two VI points, and we can match it to, well, what are the easy ones? Well, probably those intercepts. Those two intercepts, let's find those, and they correspond to open and short circuits. So let's quickly make sure we understand that. If this is our complex circuit, voltage I, some test points on it, and we said it has this type of relationship. This point here corresponds to, if that's current and that's V, it corresponds to no current flowing. That's the test point of an open circuit, where the terminals, there's an infinite resistance connected in that box there. So I is 0, and I measure the voltage. That gives me one of those points, that VOC point there. Another one to do is short circuit it. If I make what's inside this box here a short circuit, then there can't be any voltage across. V must be 0. So that must correspond to that one. And I measure the current that flows at that point, and it's the short circuit current. And if I get two of those, they're the easy points to find, if you like. So why don't I find those two? Open circuit voltage, short circuit current. I know the equation of this line. I'm trying to replace it by some voltage source V Thev in series with some resistor R Thev. And I need to choose those two values so that I get exactly the same curve. That's what equivalence means. So if you did the same thing with that circuit, this is I, this is V, what will this value here be? If there's an infinite resistance put in here, so an open circuit, the current's 0, what is V? VTH. So that intercept is VTH for that example simple circuit. And this intercept here, if I short circuit through here, what's the current that flows? V Thev divided by R Thev. V Thev divided by R Thev. So how do I make those two curves the same? What should I choose for V Thev? Have to make those two curves the same. VOC. VTH must be chosen to be VOC. I need to make this point here equal to that point. So V Thev should be chosen to be VOC, the open circuit voltage. I also have to match these 2 points. I need to make V Thev on R Thev equal to ISC. In other words, I choose R Thev to be equal to V Thev on ISC, which is the same as VOC on ISC. That makes the slopes of them the same. Okay. So I find my open circuit voltage, I find my short circuit current, I make the Thevenin voltage equal to the open circuit voltage, I make the Thevenin resistance equal to the ratio of VOC and ISC, I cannot tell those two circuits apart now. I can replace that complex circuit by that, and it will behave exactly the same no matter what else I connect up to the terminals. That's the power of Thevenin's theorem. Okay, quick great invention. Do you like to dream? Like to dream? This thing is great because this is Takaro's Kobo Dream Machine. It comes with a fragrance dispenser, soothing music and voice recorder to stimulate the dream of your choice. You are not at the mercy of anything else that's happening. You can put the fragrance of your favourite, your favourite aftershave if you want to dream about a particular boy, or Rick Astley music if you want to dream about the 80s when you had something to offer the world, and so on. So I highly recommend this device. My dream, well, you can probably guess, is I'm still, given how the Kangaroos played on the weekend, I reckon I'm still a chance. Here's a question. It says, use Thevenin's theorem to find V0. That's a poor question. Let's say I'm going to change the question to find the Thevenin equivalent of the circuit in the box. And then I just have to add on the 6K resistor. If I replace that thing in the box there, or the funny wiggly box, by the Thevenin equivalent, it's going to be pretty easy to find V0 by a voltage division, because I'll have a voltage source, two resistors, all in series. So the real question is, find the Thevenin equivalent of that circuit there. How do I do it? First, find that voltage. We already did that. That was your first MELTS question. VOC equals 9 volts. Work done. You did that already. The second part, you short circuit it. You find that current. That was the second thing you did today. ISC you found was 3 milliamps. We're done. Choose V Thevenin equal to VOC equals 9 volts. R Thevenin has to be VOC divided by ISC, which is 9 volts divided by 3 milliamps, which is 3 k ohms. VThev and RThev. They're the values you should choose, and the behaviour of that simplified circuit will be exactly the same. It means I can replace all of that by this, plus minus 9 volts, 3 k ohms. That's that. Now I'll put the 6 k ohm resistor on it, and I ask you to find V0. V0 equals what? 6 volts. Case closed. You're all over Thevenin. Very good. There's another way to find the equivalent resistance of a Thevenin resistance. You can look into the terminals and zero all the sources, and then just find the equivalent resistance of the resistor network. Okay. So here, I make the current source an open circuit, I make the voltage source a short circuit, and I'm left with this. And I say, what's the Thevenin equivalent of a series combination of 2 and 1? Well, it's 3 k ohms, just like we got previously. But there is a warning. If you have dependent sources in there, someone mentioned, can we do it with dependent? If you do, you can't do this, because just like before, you can't just zero a dependent source. You know, in superposition, we had to leave them in each time. Similarly here, you can't zero a dependent source. So in that case, you would have to go back, calculate VOC, calculate the short circuit current, and take the ratio. But if you only have independent sources, you can do this. Thanks for listening.